Okay, hello. Today we're going to talk about electromechanical systems, electric motor. Really, we're going to do an analysis of the electric motor. You should have this printed out so you can make notes if you'd like to. I'm going to try and go through and do some explanations myself. We're going to try and get a little bit of introduction to some block diagrams and that sort of thing too. So this is my schematic diagram of an electric motor. And what you see is that we have the electrical parts of the electric motor. Those are the parts. This is the motor windings representation. So the motor windings are wires wound round and round and round the armature. Those wires have an equivalent resistance. There's an equivalent inductance with those two. We're going to ignore that inductance, but there's two things that happen. One of the things that I want to just point out here is that when we put some current through this motor, the current flows through this way. We're going to put the current flows through that way. And one of the things that happens is when you have, so what we normally will do is we'll put like a magnet next to our armature. The magnet will have a north pole and a south pole. And when we have current flowing through a magnetic field, it generates a torque. So you can go back and look at your physics books for some of that. And so what we're going to do here is we're going to look at the electrical parts of the motor, then we're going to look at the mechanical parts of the motor and how they go together. So just so you know, this is very similar to the electrical motor schematic that Norman Nice gives to you also in chapter 2. His is a little bit different. You'll notice that he's already ignored the inductance, and I'm going to ignore the inductance, kind of wave that away first, and we'll talk about it more in depth later. But you'll also notice that in his particular case here, he represents his gears as kind of like flat things. And I like to represent my gears a little bit differently. But we also see here that we have the armature. I'm trying to write with the mouse. I'm going to have to try and give that up. So the armature, and then there's oftentimes an output load that we're going to have there. So he has that also. We'll talk a little bit more about what his torque speed curve means, but for now we're just going to find out what the motor parameters are. He gives this to us so that we can find the motor parameters ourselves. Okay. So let's go back to our motor. What we can see is if again, I mentioned we're going to have, if we watch current flowing, so there's two sides of a motor. One is when we push current through the motor with our north and south poles, it makes the motor go. But there's another side to the motor which says that if I grab a hold of the output shaft of the motor and put a disturbance torque on that motor to make that motor move, it also generates a voltage across the motor that we're going to call the back EMF. And that back EMF voltage, what we're going to do is that back VEMF is equal to, it's the back EMF motor constant, KE, times the velocity of the motor. So theta dot, sorry, my theta dot isn't very good. Theta dot, sorry about that. All right, so we've got that. So for mechanical engineers, we break our pieces down into smaller pieces. Let's just look really quickly here at the electrical operation of the motor. So what we can do is we can sum the sum the voltages across. So we have an input voltage. We know what the voltage is going across the resistance of the motor, that's IR, and we know what the voltage is that's generated by the inductance, L di dt. And then there's also this other back EMF voltage that I've talked about. It opposes the motion. So this opposes the motion. This opposes the voltage that I apply. This opposes the voltage that I apply, and this opposes the voltage that I apply. Back EMF is here. And what we can do is we can just sum those things. So I've actually just summed those things and taken the Laplace transform. Again, I'm going to say, oh, initial conditions are 0, and so here's the Laplace transform. And here with equation 3, I think it's instructive for us to talk just a little bit right now before we go on to equation 4 and make a big mess of it. Let's just talk a little bit about block diagrams.
Okay, block diagrams. I love block diagrams. So one of the things about block diagrams, we're going to just kind of do some drawing and writing and that sort of thing. And so what we'll do right here is let's just write down that equation of motion again. That's Vn. Vn is equal to I times R m plus L di dt plus V EMF. Now, we're going to take the Laplace transform of that right away. That's going to be I Rm plus LSI plus V. Let's do it this way. Let's change what V is. That's KE times S theta of the motor. So that's how fast is the motor going itself. Now, for block diagrams, one of the things about system analysis is that we're always going to try and solve our equations for the highest derivative. In this particular case, we have a little bit of consternation here because there's two variables that have a single s on them. Oftentimes you're not faced with this, but in this case there is, and now I'm just going to tell you that you're going to use your experience and say, oh, okay, what I'm really looking for is the current. I'm looking for I. And so what I'm going to do is I'm going to solve for LSI is going to be equal to, so that's a Vn. That's kind of the input. We kind of know that. Minus IRm minus Ke times S theta m. And so now we have a perfectly good equation. What I'm going to do is I'm going to convert this equation into a block diagram for you. And so the first thing that we have to know about block diagrams is, that they're just a block. So let's look here. We're going to have a signal, Vn, and we're going to have a little arrow that represents that signal. And that signal is going to go into a block here. So, well, the first thing we're going to do is we're going to make this, we're going to put in a summing junction. And what we're going to do is we're going to look here and see that what we've got is a minus sign here. And what we're going to want to do here, I'm going to kind of, because I know how this works, I'm going to change the order a little bit. We're going to put in this variable, which is Ke S theta m. So we're going to put that variable in. That's got a minus sign by it. And we're going to put this variable in. Also, this has got a minus sign by it. And that's going to be I times Rm. Okay, so in block diagram algebra, as long as we do these things, once we do these things, then what comes out of this summing junction right here, what comes out of that summing junction is LSI. All right, but really what we're trying to solve for at this point, we'd like to solve for the current. We'd like to know how much current is going through the motor. We're going to do that because the current, if we multiply the current times the motor torque constant, we'll know how much torque the motor is putting out. And so for block diagrams, what we get to do for block diagrams is we put in a block. And what we're going to do, we're not interested in, we're interested in 1 over L. So we'd like to do 1 over L because what that's going to give us is S times I. Now I'm going to warn you that when we're going into MATLAB and Simulink later, MATLAB and Simulink were designed by electrical engineers, and even though this is called block diagrams in MATLAB and Simulink, they don't use them as a block diagram. They use triangles because electrical engineers all know that the way you put a gain into a system is using an operational amplifier. And the triangle like that is what is the symbol for an operational amplifier. So it's going to be a little bit different. You're going to have to pay a little attention. When I use blocks, MATLAB and Simulink are going to use these kind of symbols, okay? So now that we've got LSI, what we're going to do with our LSI, let's just see what happens with our LSI. What we're going to do is, oh, you know, we're not very interested in SI either. And so what we'd like to do is we'd like to multiply by 1 over S, right? And if we do that, aha, now we get I coming out. And so now we can be done. We can be completely done with this, except that I noticed that there's kind of a connection here that I can make. I'll put a dotted line here so that you'll know that I made this second. And what I can do is I can say, hey, you know, there's a connection here that I can make. And the way block diagrams work, again, if this is I, and what I want is I times R, then what I'm going to do here is I'm going to multiply by Rm. Okay? And so this one right here, I don't have all the pieces to put this one in yet, because you see what I need here is I need to know how fast the motor's going, and we're not to that spot yet. So I'm just going to leave the block diagram here for 1 second. I'm going to come back to this block diagram. I believe I'm going to come back to this block diagram specifically. But first, what I'm going to do is I'm going to make a little bit of a change to this block diagram. So give me a break here. Give me a little bit of a minute. And what I'll do is I'm going to redraw this block diagram. So it turns out that in all systems, this is the standard form for block diagrams. Ta-da, here's the standard form. And in any book that you pick up on controls, the standard form of the block diagram is that we're going to have G of S. So G of S is a general transfer function, input to output. And what we'll often call this is the feed forward. That's the general transfer function. General transfer function, sir! All right. Almost always the output is referenced as C of S, so that's the output. There's oftentimes there always is, there's a feedback part of it, which is called H of S. This is the feedback part. We'll put a little dot here. We'll put our little arrow going in here. So, and then what we're going to do is we're going to see that also there's often a summing junction. Now, the summing junction has some kind of an input. They call that the reference signal, R of S. And oftentimes they'll call this the error, E of S, but those are just names. Now, this almost always has a plus sign. It doesn't have to, but this one is important. This is going to be either minus, or sometimes it can be plus. And what I'm going to do is I'm going to carry both of those signs around with me as we go through the block diagram. So every controls book has this block diagram in it. And then one of the things about it is that when block diagrams have a lot of blocks, that's not what you want. You want to boil this down to its constituent, just a single block, just a single transfer function. And what we see here is that we see that there is a loop. Loops are going to get you all excited. Loop! Hey, it's a loop! And what we're going to do is we're going to recognize that in any loop we can reduce that loop to an equivalent block diagram that is much simpler looking than just this. So we're going to look for the transfer function that involves the input R of S and the output C of S. And so just by looking at the block diagram, and even with our limited knowledge about what how block diagrams work, we can see that C is equal to G times E, because we know that's how block diagrams work. We can also see that E is equal to R minus, or plus, depending on what that sign is, R minus H times C. So just a little bit of substitution can help us here. This is going to be C is equal to G times R minus H C in parentheses. We're going to do a little bit of algebraic manipulation here, and then I better do my algebra. This is G R minus G H C. And now I'm gonna say C. So I'm interested in what comes out. So I'm gonna say C plus, oops, I forgot to carry along this, plus or minus, C plus or minus G H C is equal to R times G. So I'm just doing a little algebra here for my loop. And now what I'm going to do is I'm going to take out the common factor. This is going to be 1 plus or minus GH is equal to RG. Now, almost always what we're looking for is we're looking for the transfer function, T of S. So the equivalent transfer function just for this loop, T of S, is equal to the output over the input. That's always the case with the transfer function, output over input. And what we're going to do with that transfer function is we're going to say that is going to be, so let's see, what is the output? Is going to be C, and what is the input? That's going to be R, and that's going to be G over 1 plus or minus GH. And so this is one formula that you can remember, that you can decide to remember. And the way that is it says the equivalent transfer function is the feed forward. The equivalent transfer function for a loop, T of S, is equal to the feed forward divided by 1 plus or minus the feed forward times the feedback. Ta-da! So that's block diagrams in a nutshell. There will be more of it later. Okay, then, let's get back to the block diagram that we just made for our electric motor. And, be still, my beating heart. What do I see here? Oh, I see a loop. And I want to reduce that loop into an equivalent transfer function. And good thing for me is that I know what the formula is. And so I can tell you, I'm going to give you, let me take one little bit step back, and I just want to talk a little bit about this summing junction here. All right, so what we see is that this summing junction, it has two things going into it, plus, minus, minus. Okay, and then it's got some output. And what we know is that when we do the addition operation, that operation doesn't matter what order you do it in. So here's an equivalent way of writing that. I can put two sums, plus, plus, and the output, and then I can put the minus there, and I can put the other minus there, okay? So those are the same things. And so kind of in my mind, when I saw the loop, I kind of already did that. And now I can see that I have a loop. a loop, be still my beating heart. So since I know what the formula for a loop is, I'm just going to go ahead and I'm going to put that, I'm going to write the equivalent transfer function for this loop down here. So it's the feed forward. So the equivalent transfer function, I'm going to call this T1. Sometimes transfer function, the T, is used for the overall transfer function, so you have to make some distinction between these intermediate ones that we're building. It's the feed forward over 1 plus the feed forward times the feedback. Now, if this is one you can memorize and you should already know it. Feed forward, 1 plus feed forward times feedback. And you can do that easily. So the feed forward here is 1 over LS, and the feedback is going to be 1 plus, so it's the feed forward, 1 over LS, 1 over RM. And oftentimes what happens is you get these things on the denominator here, and if you go back in, your math teacher back in high school would whack you upside the head if you left fractions in the denominator. So actually what we're going to do is we're going to clear this fraction here, this 1 plus something here. So we're going to clear this fraction. This is a common thing that you have to do, because I'm going to clear the fraction 1 over LS, and then I get it this way. It looks like this: 1 over LS plus RM. Now, I'm going to do just one more math operation here that I think is going to help you guys out a little bit. I'm going to take out a factor of RM, 1 over RM, and this is going to be 1 over RM divided by L over RM S plus 1. So one of the things that I see right off the bat is that this part of it, oh, sorry, this is not right. This is just a 1. Sorry, I had to grade that one. I already took the 1 over RM out. I've got it in here. I don't need to put it also up there. Okay, so one of the things is like, oh, wait, this just looks like a first order system. First order system. And here is the time constant, tau is equal to L over R. Right? And before we go too much further, let me just make sure that I'm going to draw this block diagram one last time here. That's not one last time. I'm going to keep drawing this block diagram until everybody's sick and tired of seeing that block diagram drawn over and over and over again. And so now what we're going to see here is that I'm allowed to replace that block diagram, this loop up here, I'm replacing it with some simpler blocks, some more compact dynamic blocks. This is 1 over tau E S plus 1. I'm going to call this tau E. That's the electrical time constant. And then what I get out of here is I get the current I. Now, it is true that I still have this thing floating around here. This has got a minus sign on it. This is a KE. This is the back EMF S times theta M. So that means how fast is the motor moving. So there's a couple of different ways we can do it. The motor generally is going to move slower because it's a physical thing. It's going to move slower than the electrical parts of the system. And so one thing that I can kind of do is just kind of ignore that. What I'm looking at here is that, and certainly when I start the whole system, I can say, oh, well, this is stopped. And so now what I'm going to look at is I'm going to look at a unit step input of the voltage. So I'm going to put a 1 volt input in here. This one happens to be 0 right now because that 1 volt input hasn't flowed through my system yet. So this is just a gain. All that does is changes 1 volt into some other number. And I'm not even sure I know exactly even what to call that variable right there. I don't really care. We're just looking at math anyway. But one of the things that I can do is, because I've done first order systems often enough now, if I look at time, I can draw how the current comes out for a first order system, what the current looks like. Let's see, tau, 2 tau, 3 tau, oh, I should have drawn this a little longer, 4 tau, so that 4 times the time constant. And what I know is that the current starts out at 0. At 1 times the time constant, it moves about 63% of the time. and then it goes closer and closer until it gets to whatever its steady state output is. In its steady state output, let's see, it's 1 over Rm. We're going to have to talk about that. We'll do that in class, 1 over Rm. But what we see is that, yeah. Now, you notice that I haven't put any actual time values along this axis. All I've put is some taus. And then what is tau? Tau is L over R. So for a typical motor, Rm, typical motor, Rm is around 3 ohms, something like that. You know, you're going to be in the 1 to 5 ohm range. Sometimes they get a little bit better than that. And the typical inductance L is 3e minus 6 henries. I don't know if you do it IES or Henry, because that Henry's, that means it belongs to Henry, and then just putting, anyway. So the bottom line is that whatever, if I'm going to draw a little bit different representation of the time response of this, and I'm going to put it like this is like in microseconds or something like that, right? Because that's times 10 to the minus 6. There's some milliseconds or something like that, micro, milli, jilly, vanilli, I don't know what. But for the most part, you know, what we understand is that if we're looking at time here, something with a very slow time constant is going to look like that, and something with a very fast time constant is going to look like this. And now I'm going to draw one last little thing here, is that, you know, in the time space of typical mechanical systems, what I'm looking at is that, hey, well, that pen didn't work. Hey, this thing, I'm going to compare this with what does so this is a fast first order, and I'm going to compare this with a pure gain, G-A-I-N. How do those look? Oh, it looks like this. A pure gain just looks like that. Well, you know, am I going to quibble about this stuff right in here? You know? So my point is that when there's a fast time constant in it, it's possible that I can neglect these dynamics. And that's what I'm going to do.
Okay, so now I'm going to give you a little bit of time. You can go get your little sheets on analysis of an electromechanical system. We're going to talk about that a little bit more now. What we'll do is we can see here, remember we were right here, we've written the electrical system equations. We've got the current, we solved for the current, and we noticed last time that this, the loop parts, so one thing was, so there's a couple of different ways of looking at it, right? So one is that, we did a block diagram and we could see that the loop made this dynamics that's in the denominator here more or less okay, you're allowed to neglect that. But another way to look at it is that when R is big compared to L is very small, like R is 1 and L is 10 to the minus 6. So essentially you're multiplying this S by 0 anyhow, right? And so if you're just multiplying that S by 0 anyhow, then you can just get rid of it. Boom, it's gone. And so then we're left with equation 4a. which is the electrical part of the system. All right then. So now we're going to talk about the mechanical operation, and I know you guys who are electrical engineers don't like to see this sort of thing, but what we're going to do is we're going to do free body diagrams for the rotational part of the armature. And as always, what the forces, the torques that we see are analogous to the forces that we had on the mass spring damper system. And those forces and torques, those look like this. So here's what we've got. We're going to have, sorry, I'm butting around on the sides here. We're going to have an input torque, and so the input torque comes from the motor torque constant. Did I already say that up there? Now I have to go back and look. Oh, I did not. Okay, so we're going to have an input torque. So somehow what happens is that as we put current through that armature wiring, what happens is that we generate a torque on the armature. So we've got an input torque. We've got I see that there's an SIGN thing here. Oh, right here. I'm going to fix this. So before you get your copy, that's going to get fixed. So one of the things is that let's just go over some pieces of mechanical system stuff here for you. But let's just look at which direction positive things are. And so what ends up happening is you guys who are electrical engineers, you're not going to have to much worry about these sorts of things too much. But what we see is that this one is moving in this direction, and then when that one moves in that direction, this one moves in this direction, right? So what I would like to do is I would like to pretend like whatever voltage I put onto my system, that it tends to want to move my armature in what I have already established is my positive theta direction. And I've also established the output gear. You'll see that's a different direction, but that's just because if I move this one in its positive theta direction, if I move it in the positive theta direction, then that will also move my output gear in its positive theta direction. I've also put an external load on here. So there's two ways you can get an electric motor to move. One way is to put a voltage to it and then it'll move. And another way is to grab a hold of the output shaft and just push it, and then that makes it move too. So I've also put that electric motor, I've put that, shown my force D in the direction of the positive datum. I'm going to get rid of those. All right, so I'm seeing as I'm working here is that I have inadvertently put a negative number here, and I'm going to fix that for you right now. Right? Because I'm going to make this move in my positive direction. Now, the reason, and I can see, I don't know how these dots got, that's supposed to be theta double dot, right? Because it's the inertial load, it's the rotational inertial load. It's defined by the moment of inertia times the rotational acceleration. And this is also has to have a dot on top of it. That's the I better put my dots a little bit bigger here so you can see them. I'm going to fix that for you too. You can bet I'm making a list here. And all right, so what we can do is we can just sum the moments around this axis. Sum the moments around that axis. And what we get is the torque of the motor is equal to J theta double dot plus B theta dot M plus R1F. So what I've done is I've replaced the external force that one gear of my motor is applying to the other gear in my gear train. So I'm just saying, oh, there's a linear force here. I multiply it times its distance R1. I multiply distance to make it. And so that's one of the equations of motion that we have there. taking the Laplace transform is easy enough. We're going to know that the motor torque constant, the way you generate a torque with a motor is you put in a current, you multiply it by a motor torque constant Km. That's how many Newton meters per amp you get. And then what we're going to get is we're going to get a torque coming out of the motor. Now I'm going to draw a free body diagram of the other gear. I'm going to draw a free body diagram of the other gear. You'll notice here that I've just put I put an equal and opposite force on that gear tooth, if there was a little gear tooth right there. Again, I don't know what happened to my dots here. I'm going to go back and look and put those in. I think I can see them. Somehow my equations got all mixed up somewhere, but I'll put them back in for you. All right, and so what we're going to do is we're just going to say, okay, we've got a D. It's moving in the same direction that R2 times F is. We've got output inertia and output damping. Again, that might be the grease on the bearings or something like that. We're going to put those together and get our, do a little bit of algebra here, blah, blah, blah. We're going to do some algebra. And we're going to notice that in a perfect world, the gear train all moves as one piece. And so if I look at R1 times theta of the motor, that also equals R2 times theta out, right? So what we can do is we can look at if we have, I'm going to draw over here. So if we have one, I don't know what that was. If we have one gear and we have another gear, and I'm going to change colors here if I can do that to green. So if that one moves that far, this one moves by the same distance. So one is R1 times theta m, and the other is R2 times theta out. And so now what I can do is I can generate this relationship between the output gear and the input gear. That's not, if your gear teeth are not rigid, that is not the case. And so you may have to think about that, and I'll tell you times when people do think about that. So now I can just go through and I can do blah, 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 a bunch. Now, here's what the important part of it is. I've got a voltage that I apply. I've got the motor torque constant. So really what kind of happens is I put in a voltage, I divide by the resistance, and that kind of gives me a current. Then I multiply by the motor torque constant, right? That gives me a torque. Now, the reason that you put a set of gears into your system is so that you get a gear ratio, R2 over R1. In this case, R2 is bigger than R1, so that means you get more torque out than you put in, and that makes sense. The motor armature just generates a little tiny bit of torque. You can stop that with your fingers. But once you put it into a big gearbox, you can't anymore. And what we see is that there's also an output. So I can either make it move by putting in a voltage, I can make it move by putting in an external disturbance force. And then what we're going to see is that we've got some dynamic pieces of it over here. So on the output shaft, we've got here's an inertial characteristic, an inertial term, that's times theta double dot, and a damping term, that's times theta dot. That's what the single S is. And here's an important piece of it is that, if I look at this, whatever the output inertia is on that output gear, whatever it is, then what I have is, that's whatever I measure that inertia. The input inertia, the inertia that I see from the motor, now that's reflected to the output space by the gear ratio, but the gear ratio is squared. And oftentimes you put a very big gear ratio in. And so what that means is that when you put in a very big gear ratio, you actually really increase the effective inertia of your armature. Now, the damping part of it has 3 terms in it. I want to point out these 3 terms. So there's one part of it, this is the damping that's on the output shaft itself. So if you hook this up to a giant wind turbine, and then it may have some damping on there. But if it's just a bare shaft, then that damping might be equal to 0. This is the damping that's at the motor itself. So maybe this is just due to the WD-40 that somebody squirted onto the ball bearings that hold the motor shaft. And that generally is small, but here again, you have to be careful because you multiply by the gear ratio squared. And then what is this term over here? I have an RLS, and we ignored this RLS stuff already. So let's just don't even bother with that. That's just 1 right here. But let's look at what this term is. This term has the KE. It's the back EMF term. It's got the motor torque constant, and it also is multiplied by the gear ratio squared. So even if you go to a lot of trouble to physically remove all of the available, physically remove whatever damping you might have, the point that I'm trying to make here is that you will still have this damping. I'm getting rid of that. I have to go back and look in my math of where I got rid of that, but we don't care about that stuff right now. And so with those assumptions that we've made so far, then here's what we're going to do. We've got this equation for our motor. And what we see is that we put in an input motion, and there's some dynamics that are associated with it.
All right, so we still have a pretty good equation of motion. We're going to look at the dynamic equation that governs the motion of an electric motor. And we've gone through all the analysis and stuff. We know that there's a disturbance torque. There's 2 ways to make our motor move. We can either put in a disturbance torque on the output shaft, or we can put a voltage to the black and red wire, Km over Rm. This is the gear ratio, R2 over R1. That's for standard spur gears. Sometimes people will call that the gear ratio N, or I can't remember. I'd have to go look at all. It's 1 over N, who knows. But sometimes they just call the gear ratio R2 over R1 is the gear ratio N. And so then what we've got is we've got theta out, and we've got J equivalent S squared plus B equivalent S. Now, that's perfectly good if we're looking at wanting to know how the motor position changes with time. What I'm going to do now is take 1 step backwards and make this S theta 0. This is going to be J equivalent S plus B equivalent. So what I've done here is I've made this be S theta 0 equals omega 0. This is the output speed. Right? So now we're looking at the output speed, not the output position. We'll look at the position again, but for now I'm just going to look at the output speed. And so here again, what I'm going to do is I'm going to solve this equation for the highest derivative. In this case, the highest derivative is going to be omega S J is equal to D plus VI Km over Rm, R2 over R1, minus B equivalent. So we've got an equation, and if I wanted to make a block diagram with it, I want to emphasize now that part of the reasons that I'm going to do block diagrams is that's what Simulink is. It does block diagrams, and we'll learn how to do that a little bit more in lab. But let's look and see how we're going to do this block diagram for J equivalent. Well, I'm going to go ahead and say, oh, you know what? The input voltage, intuitively I'm going to say, oh, that input voltage is kind of what I put in here. It's the input voltage, Km. And so now what I'm going to do is I'm going to say, oh, you know what also can happen here is I get a 1 over Rm. That more or less converts this into current. And I'm going to just write down the variables that I expect to see in between each of these blocks. So then I'm also going to have like the motor torque constant Km. And so that puts the torque That gives me whatever torque I have at the motor. I'll write that in. And then I'm going to do the gear ratio, R2 over R1, and this gives me the torque at the output shaft, right? Like sometimes you can put little arrows there. And then what I see is that, you know, it's this point right here where I might have the wind blowing on my wind turbine or my fan blade, and that is where I might have to have a plus go in there. I'm also going to now, you know, I could put both of these in the same summing junction, but I'm not going to. I'm going to subtract off this term here, that's B equivalent times, so really, I really need theta out here, and I really need a theta out here, right? So I needed to distribute that. Oh, no, sorry. Oh, omega. I already have omega here. I should put omega out, sorry. My bad. Omega out. This is B equivalent times omega out. So this is kind of like this junction right here is kind of like the sum of all the torques at the output shaft. And so what I'm going to do, mathematically, if I do that, what that gives me is omega out J equivalent. And as we talked about earlier, I really don't want omega out J equivalent. I'm going to multiply by 1 over J equivalent. That's going to give me omega out times S. And again, I don't want omega out times S. What I really want is I want omega out times 1 over S, which is omega out. Ta-da! Oh, you know, as long as I'm working here, I might as well just go ahead and finish this. I've got omega out, and I might as well multiply it times B equivalent. All right, so this is something, we'll do this in Simulink, but what we can see is that this is a way of expressing exactly what's going to happen for each part of our motor. All right, and so now what I'm going to do is, you know what? It turns out that there's actually two ways that I can, you know, in linear systems, I'm not allowed to have two inputs. I'm only allowed to have one input at a time. And so I can say, oh, you know, here's one of the inputs. Here's one of the inputs. I'm going to do this block diagram a different way. So this is a Km over Rm, R2 over R1. And then I'm going to have, okay, I will do it in two different parts here. I'm going to do it in two different parts. 1 over J equivalent, 1 over S. This is omega out. B equivalent plus minus. And then another way I can do it is I can say, you know, I'd like to see what the transfer function is that relates my disturbance D. And so what I'm going to do in the disturbance D is I'm just going to say, oh, I'm going to pretend like, in this one, I'm going to pretend like the disturbance D is 0. And in this one, number 2, I'm going to pretend like the input is 0. So that just goes away. And again, I get 1 over J equivalent S, omega 0, B equivalent. And remember, B equivalent could be real damping or it could just be just the electromagnetic damping in the motor itself. In both of these cases, I see a loop. Oh, I get so excited by loops. And I can reduce that loop. These loops, you'll see they're both the same. So I'm going to reduce the loop. It's 1 over Js, the feed forward, divided by 1 plus the feed forward times the feedback, and I'm going to clear that fraction to get an equivalent transfer function for both of these loops. The equivalent transfer function is going to be 1 over JS plus B. So I can just replace those by 1 over JS plus B. So what that allows me to do then, if I want to, I can look at what this is. This is T1 of S is going to be the output over the input. In this case, the output is omega 0 and the input is VI. And I can write that transfer function easily. It's Km over Rm, R2 over R1, divided by JS plus B. These are the equivalents, sorry. J equivalent, B equivalent, S plus B. And then I can also do this one if I want to. This is a T2 of S. T2 of S is equal to now the output over the input, which is the output is still D omega 0, but now the input is D, my disturbance, and I can say, oh, 1 over J equivalent S plus B. So I can, either one of those two transfer functions, I can run those in using MATLAB's step command, and I can see what the output is. I've given you some numbers that go along with those, and so what I'd like you to do is I'd like you to see what the response for a unit step input for both of those inputs is. Okay.